looks like a very simple question, but we only had 4 volunteers for answers and they all differed. Only 2 people agreed. Okay. Any other answers in the last minute? No? Oh, somebody is furiously calculating, so we'll wait. Okay, so these problems, you can continue to calculate if you want. But so these problems, they appear quite intuitive. And I think that's the problem with probabilities. We try to use our intuition rather than what we know about probability. So actually, it's very easy to get these problems wrong unless you write them properly. Okay, so we're going to write this down because we're going to see something in this problem that we haven't seen before so far, right? So the data given to us is what is the probability of finding a male, right? And we know this is 0.52. We know what is the probability of finding a female, 48. We know what the probability is that if you find a male, that they speak Kannada, right? Do you know how to represent this? Conditional probability, right? So if you're given a male, so what is the probability they speak Kannada given that they are a male? This is 0.36. Similarly, you know what is the probability of, so this is conditional, right? It's not really a division. So what you're saying is, if you know that you've drawn a female sample, what is the probability they can speak Kannada? This is 4.42, right? And what do we need to find? We need to find the probability that if you choose a person and they can speak Kannada, so we know they can speak Kannada, what is the probability that they are? Okay, so how can we calculate this? So there are some. So wait, the numbers don't really make sense at this point, right? So we can substitute the numbers at the very end. The probability that you have a male given they can speak Kannada is the probability that they can speak Kannada given they are a male times the probability that it is a male divided by the number of Kannada speakers, right? So the total number of Kannada speakers is probability of this times the males plus probability of this times the number of females. So actually, if you think of it now intuitively, you see this is the number of Kannada speakers and this is the probability that it's there. Okay, so this is the prior information, right? And what is this called? Okay. So now actually that depends on your view. So let's leave it at this. The prior information given if you draw a random sample of a male is there, P of m. Okay, so now how many of you did this? 1, 2, so all of you did this. Still you didn't get the answer. Okay, that's okay. Then there's a different issue. So that's fine. Okay, so this conditional thing we haven't seen so far, right? We looked at it briefly in terms of correlations. We said if you have a random variable that depends on another random variable, then there is this idea of conditional probability, which means What is the probability that both A and B happen divided by probability of B? Okay. That's what conditional means. So what happens if A is independent of B? There was a question in the initial assessment where you had 3 dice, or dice was rolled 3 times, right? And I asked you, what is the probability of getting a 4th 6 given that you had 3 6s? Right? In that case, it didn't matter how many 6s had been rolled. The next roll was independent, which means the probability of A intersection B was 0. So right? Or what it was just P of A in that case. So you should have just got P 1 over 6. Okay, but anyway, the point here is if they're independent, then it's easy. It's just P of A divided by. But in general, we don't know when we look at random variables, it is not trivial to know whether 2 events are dependent or not, especially if they're tied to an application. So if you just see how random numbers are drawn and you can see the code, then you can just look at it and know maybe, if the code is not too complicated, that they're related. But if you're doing some application and you've done generated some things, you've mapped them through some functions, it's very hard to know if they're correlated. And typically what will happen is you will draw X and Y independently in 2 different places, but somewhere there will be some function G. Now you will get G of Y here and G of X here, and these two might end up being, G of X and G of Y might end up being coupled just because you pass them through some function there. Right? This is quite common in applications. You end up with these kind of dependencies. So in that case, it's important to know how we can go back and forth between this conditional and this. And this, of course, is called Bayes' theorem. And you've probably heard of Bayesian statistics. And this is sort of the fundamental idea which you need to know for all of that theory. I just wanted to check if you guys know this. Looks like all of you know this. So that's good. So then I will cover 2. So should I do this? Okay, so then since you know this, we can go to. Okay, so now let's take a quick look at this importance sampling business, right, that we've been discussing. We discussed importance sampling. What did we do in importance sampling? You had some function like this, and we chose an importance function. Maybe in this case, let's say we choose an importance function like this. So this is G of X. Is this a good importance function? The red one? Or is it bad? This is an importance function, G of X. This is the integrand f of X. What does importance function mean? It means that we are going to use inverse CDF or rejection to generate samples. And we are going to integrate f of X using those samples. Okay? So in the case that we saw before, what we did was we had I equals integral of x dx, and then we wrote mu equals where xi were uniformly random, and we wrote an importance sampling estimator which was do you remember this? So in this case, xi is distributed according to G of X, and in this case xi is uniform. We had 2 different estimators. This is the importance sampling estimator. Now, if I use this particular red function as the importance function, then I'll get a lot of samples here, right? Is that a good thing or a bad thing to integrate f of x? It's not obvious? Well, so where is the value of f of x really high? You're going to get very few samples here. So it's not going to be a good estimator. Most of your samples, if you remember the histogram in your lab, will end up here, and you will totally sort of not hit this. That doesn't mean you get the wrong answer. In expectation, you will get the right answer, but your n will have to be very large for you to get suitable representation here of this part of the integrand, right? And the reason you can also explain just mathematically rather than intuitively, because our estimator is made up of this, right? If g of x is very low, where f of x is really high, then this number will be very high, right? F of x will be large in this part. G of x will be very, very small. So 1 over g of x is very large. And then when you multiply, you get a really large number. So what will happen is some samples, very few of the samples landing here will have massive spikes. And most of the samples that are here will have some low value. What does that mean? So if you look at the first sample maybe here, second sample. So these are the values of each. So this is f of xi divided by g of xi, right? And this is, let's say, I. Okay, you have I equals 1, 2, 3, and so on. And you'll get most of the samples here, and then there'll be this one spike, which is somewhere here, maybe here. As a result, the variance of these values will be very large. So the estimator is not that useful. Like you saw in the rendered image, you'll see a lot of dots. So in these spikes, we don't want. One way to improve that is to move the importance function here, right? So in general, if you already knew some prior information about this function, you could do that. However, in this bimodal case, it's not obvious how with the unimodal function, you may get something useful. Can someone suggest, so given that we just spoke about correlations and all that, and now that I've spoken about importance sampling, can someone suggest how we can remove this problem? So one way you could do this, which is very, very popular, is, all this again, rather than having one importance function, right, you draw the first sample. Let's say the first sample was there. Okay? Let's say that was x. To get the next sample, x, so let's call this x0. To get the next sample, x1, you use this function, but now instead of just having g of x, you condition it on x0, which means this importance function now doesn't only depend on the integrand. You may want to choose it suitably for the integrand, but you will also want it to depend on what your sample was. Okay? And then next, you will sample xi. When you sample xi, sorry, x1, right? It should have been x1. When you sample x1, you may have a different distribution around x1. Okay? And you use that to sample x2. This is g of x given x1. Is that clear? Rather than having one importance function, which is what we did there, one strategy would be, if you're, so the thing is, remember, to get important samples, what did you have to do? You had to invert the CDF and all this business, or even if you had to do rejections. So you want some importance function that's easy to sample from. You don't want a very complicated function here. On the other hand, the integrand can be very complicated depending on your application. Right? So here, now what we've done is we've kept the simple importance function, but somehow we make that function dependent on where the sample is centered, and we keep moving the sample. Well, so each of these is a sample, but obviously only on, yeah, exactly. It's, yeah, exactly, that is crucial, that this sample here is critical to prove certain properties, that this sample here does not explicitly depend on x0. It probabilistically may depend, but explicitly, given x1, you can completely write what x2 is. Huh? No, it need not be, because you could have got a sample on this side. Doesn't need to be greater. So let me reiterate. x3 from x2 you might have got this, and x3 can be here. Okay, so now the dependency, yeah, so you can tailor this to any way you want. You can have x2 depending on x1 and x0, that's fine. It's just going to complicate your algorithm, and you have to prove certain properties about this, right? However, if you know, in this case, we know P of x3 given x2, right? We also know P of x2 given x1. And we know, obviously, P of x1 given x. This is all known because this is the distributions that we're using, right? Then you can work their dependencies out. But it's important that we know the relationship between consecutive variables explicitly. For example, these importance functions. Okay, so now what you've got is we've already got 4 samples, correct? And the question is, what is the distribution of these samples? That's a hard problem, right? First of all, even with the normal importance sampling, when I asked you f of x, so remember, this is sort of a side note. Some of you, when you drew a random variable in the lab, and then you squared it, instead of trying to sample from x squared. And when we asked what is the distribution of x squared, it was non-trivial. You couldn't write it down easily. Now imagine here, we are having dependencies, and we're doing some correlated sampling with all these conditional things. So if you do this, and I ask you, what is the distribution of these samples? So in other words, if I get all these samples and get the histogram, what is the shape of the histogram? That's not easy to answer, right? Just given what you know. I mean, you can work it out, but again, this is again where intuition may not really be that useful. Okay, so this turns out to be a very popular strategy. It was actually discovered in chemistry by this guy called, does anyone know? So it was Metropolis, it's called Metropolis Hastings, but Hastings sort of combined. So this is the basis of Metropolis Hastings sampling. And if you see this, in some sense, you have a chain of samples, x0. So you have a chain where you have x0, x1, then you get x2, x3. There is a chain dependency, right? Like this. And we know exactly the dependency. If you know what x2 is, you can know what x3 is. This we know between every successive pair. Right? And this is often called a Markov chain, provided it satisfies certain properties. So this whole thing is called Markov chain. Monte Carlo, okay? It's usually called MC. We still don't know how to use this sampling algorithm for integration. But what you should know is whatever we've been doing for the first 3 days is called simple Monte Carlo. You're just drawing samples, doing it. And simple Monte Carlo already was hard to analyze. MCMC is much harder to analyze. There's still a lot of open research problems in terms of analysis. And MCMC is widely used. So it's very, very rare. I mean, I would say it's very rare to find applications where people use simple Monte Carlo. Most applications, including some of the things that you sent in, use either sort of a Bayesian approach to, in that case, they were using some Bayesian regularization, or they will use Markov chain Monte Carlo, especially in higher dimensions. I'll come to that. It's Bayesian regularization. That's a different problem. Anyway, so in this case, is this clear? If you choose X, what? It doesn't matter. We don't know, right? There's just one realization. You just keep repeating this. We don't know what so obviously, Whether you get close to this depends on how you choose these curves, right? And even if you don't change them and you keep the same G, it already looks like an interesting proposition, right? So using one G and introducing these, what will the density look like? So this particular algorithm, the framework is fixed. This Metropolis Hastings algorithm is this. So that you can tailor to your application, right? So you can tailor these to your application. What is G and so on. And the algorithm provides guarantees with respect to whatever you provide as G. Okay, and it will tell you, so yeah, okay, you can see. So if you want to generate, if you want to integrate this function, right, f of x, then how can you do it? Can someone come up? So given that you've understood all this, can you suggest a way to use these samples to integrate this function? Take a minute to think. It's not that hard. Actually, this is a big jump, but once you know this, it should be okay. It's something we've already seen. I'll give you a hint. You can use rejection sampling. Okay. Okay. Okay, that's interesting. So the suggestion is at x1, which function are you evaluating? The black one? Okay. So you're evaluating that. Can you see the green from there? Yeah. So you're evaluating that green point. You get some value here. Let's call that V0 because you evaluated it to get x. Oh, wait. We are at x0. Okay, let's say we're at x1. Okay. You have evaluated it. Okay, then what do you do? Okay, so let me help you a little bit. Let's say we are at x0. We're trying to sample x1. Okay, and we do this draw, we get x1 according to this. Then you need to do some rejection. Okay, so then, like you said, you look up the function, you look up its value. But then what do you do with the value? So this part is non-trivial, right? So that's good that you have the general idea that there is some acceptance of x1 be given x0. There is some acceptance value, okay? And you're saying when you generate x1, you look up something, and if it is less than or greater than this acceptance value, you choose to reject or not. Okay? This turns out to be of x1 this will be as the notation has changed. So you take some ratio, and it's not immediately obvious how or why this is the ratio. But that was the result of this Metropolis Hastings algorithm. That if you take this as your acceptance ratio at every step, then you can achieve, what can you achieve? Rather than talking about integrating this distribution, the algorithm says if this is used as the acceptance probability, then the xi are distributed according to f of x. Okay, so what this says is you evaluate f of x and do some manipulation there to account for this local importance function. It should not be too surprising, right? If you look, actually, initially it looked like some arbitrary thing, but if you look here, you have this f over g, right? And if you look there, essentially you have this f over g and you have f over g. So you're taking the ratio of the f over g at the two locations, and you're using that as the acceptance. Okay, so this acceptance ratio leads to samples that are distributed according to the black curve, which means if you keep doing this, you take all your x's and you plot the histogram, you should get this. Is that clear? Okay, so now this is a bit interesting. In simple Monte Carlo, when we wanted to integrate f of x, we used some target distribution, evaluated the integrand, and integrated f of x. The samples were not distributed according to f of x. If the samples were distributed according to f of x, what should you do in this case? So why couldn't the importance function be f of x itself? There's only one, you only need to give me one word and I know you understood that. Okay, why can we not just choose this red curve to be the f curve? Ratio will be 1. Yeah, so what? So let me remind you again, the word starts with n. Normalization, okay, that definitely starts with n. Anything else? So why normalization? Just because it starts with n, or is there some other reason? Well, if g of x is f of x, right, every sample here needs to be divided by the integral of g of x to be normalized. You saw that already. If you don't normalize, you don't get the right distribution. Now, if you were normalizing g of x, you should know the integral of g of x. But if g is equal to f, then you have to divide by the integral of f, which you don't know. Right? Which is why we couldn't take g of x as the integrand f of x. Okay? Now here, in this process, we never needed to know the integral of f of x. All our samples are drawn here. We only need to know the integral of g of x given x, right? So x0 given x, whatever, x given, wait, I've written this wrong. Oh no, that's just the general x, okay. So we just needed to know this distribution and normalize it with respect to this distribution, which we mean it. That's the main reason why we're choosing our importance functions differently in a way that it's convenient to normalize. So we can pick these green, blue, and red curves as we want, as long as we normalize with respect to those. So in practice, what people do is they pick some nice function which is easy to integrate, easy to sample. Okay? Okay, so now you see that you can get samples distributed according to f using this algorithm without actually needing to integrate f to normalize it. But that now raises this next question. Okay, fine, we can get samples distributed according to f, but how do we integrate f using them? Can someone tell me this? If you tell me this, then I'm very happy because it means you've understood all of that stuff. Okay? It's a very simple solution. Here we couldn't generate samples from g equals f because we needed to normalize g, which is the integral of g, which is the integral of f. So we don't choose the importance function to be f of x. However, once we have samples from g, we are able to evaluate f at those samples, average them, and get the integral estimator, right? So the good thing here is we can get the integral directly by this averaging process. The bad thing is that g may or may not be a good distribution. In this case, we can generate samples x0, x1, and so on that are distributed exactly according to f of x without knowing the integral of f of x, but we need to do an additional step to calculate the integral from these. So any guesses? It's sort of the inverse question, right? So let's say I gave you random numbers distributed according to some function g of x. Okay, so once you plot the histogram, you get something like this. Okay, but I don't tell you that g of x is normalized, so it may not be normalized. I've just given you random values that give you this histogram. How will you know what the normalization value is? How will you know the integral of g? If this is the histogram is g, how do you know what the integral of the histogram is? So, you know the functional form of g of x. You just don't know the integral. Or you're also given the samples. Oh, okay, so let's first go, we don't know the functional form, but you're given the samples, let's say. So you're given, like, in this case, this is high because there are 100 samples. You know every single sample point, the location on the x-axis. Can you use that to get the integral of x, g of x? So, I mean, you look back here, when g equals f, we don't know the normalization, but what does this come down to? If g equals f, that's just 1. Which means if your samples are distributed according to the integrand, every sample in the estimator is just worth 1. Correct? So if you give every sample in this, if you remove this and just give 1 in this loop, as long as g is distributed, the samples are distributed according to f, you get the integral. So here, if you know this, then the integral of g is simply obtained by assigning weight equals 1 per sample, right? So at each part of the domain, you just have to count the number of samples, correct? To get that. Okay, so what in this algorithm, you can obtain the integral by simply assigning, because you know now the samples are distributed according to this, you can simply average them. Okay? So now the question is, well, there's a small catch. Here, this is 1 only if g is normalized. Right? Otherwise, it's 1 over the integral of g. So somehow, in this, once you get all these samples and you know that they are distributed according to p, you get something proportional to the integral, but you don't know what that constant is. And this is the problem with usually these kind of methods, is you will know the integral up to some constant. And in practice, what you could do is you could sample one point and try to evaluate what the function is here and what the function is according to you, and that ratio will help you get the integral. So that's not a big problem, but it's something to keep in mind. Anyway, so that's a detail. We can leave that out. So good. So now you've seen simple Monte Carlo, you've seen quasi Monte Carlo, and you've seen Markov chain Monte Carlo, right? And of course, you can combine QMC and MCMC, right? Instead of using random samples at each of those steps, if you use quasi-random samples, then you get MCQMC. Okay. This is probably what you will encounter in practice. So if you have some application where you need to either sample or integrate, you're very likely to encounter this algorithm. More broadly, MCMC methods. Okay, and this is going to be your question. So today we're going to have sort of a programming competition. The lab is going to be a programming, not really a programming, it's just a competition. where you're going to sample using Metropolis Hastings. And then we'll see whether you can tailor this. Whether you can tailor this intuitively, and we'll see who gets the best convergence. Okay? So what we'll have is maybe we'll have each of you present or just send me the plot with the convergence and its slope, or just send me the plots. And we'll look at different people's plots and see who got the best estimator. Okay? So I figured that would be a very quantitative way to say who did well. Okay? Okay, so that is MC. There is one more sampling algorithm. Should I tell you? Maybe I'll just give you the. So obviously this takes some computation, and it's not that easy to get correct. So let's say you have a 2D Gaussian. Let's stick to 2D. And now you want to sample according to this Gaussian. So now we want, remember you did this important sampling in 1D in your lab, where the samples were generated according to some function. Now I'm giving you a 2D function. How will you generate samples according to this? Straight away you can use rejection, right? But rejection gets more and more inefficient in higher dimensions. You can imagine if you were rejecting many samples in 1D, now if you sample in 3D, right? So for rejection of a 1D, you have to go to a 2D place samples and reject. For sampling in 2D, you have to go to 3D place samples. And in that 3D space, a lot of your samples will not be accepted. So it's highly inefficient. Can you think of an efficient way to sample according to a 2D Gaussian? Anyone? We can always do this, okay? But another technique that's very popular is to generate an arbitrary sample. And then, so let's say here, then keep one of the variables fixed. So let's keep x0. So we know here, and look at this slice, right? And what is that function going to look like? It's going to be a Gaussian, right? This is probability of one. What is this slice? So you're conditioning on x0, right? You're given x0. We're asking what is the probability of the variable x, which is in 2D. Oh, x, okay, let's call it something. Okay, so we're asking you have some variable z. Given that it has x0, what is the probability? The other variable is y0. And obviously, this is a 1D distribution. Maybe you know how to sample from it easily using your previously implemented inverse CDF. And you get y1. So then the next sample is x0, y1. Then you could keep y1 fixed, repeat the process, get this slice, and so on. Right? So you will get x1, y1. And you can keep doing this. This turns out to be very practically useful. You can prove that it has, it gives you the right distribution and so on. Has anyone seen this before? This is just called the Gibbs sampler. So in many of the papers that you'd sent me, or in the methods, you have all these terms, right? Gibbs and Metropolis Hastings and so on. This is what they mean. Actually, the underlying methods in principle are not difficult. It's the proof that this gives you the right thing is what is important. However, when you're reading a paper, it may not be critical for you to know how to prove all this, right? You just want to know, okay, why did they use Gibbs and not that? That's the important thing when it comes to an application. It does. It's just very hard because you have to invert, right? So in higher dimensions, you can. And people do that up to 2 or maybe 3. So what you can do is instead of Gibbs sampling, what you can do is tabulate the CDF, right? Or if you know it analytically, you can do it numerically, but if you know it analytically, of course you can do it. But if you tabulate the CDF, then you can numerically invert conditional and so on. But it's just a bit messy. And in 3D, it's really messy. And people still do it. So typically, as you go to higher dimensions, people switch to this MC. Okay. And a simple view of Markov chain sampling is, think of a particle that's at the origin. Okay? And let's say the particle starts moving in some direction. Okay? So let's say, okay, let's first just take an integer example. Or should we? Do you prefer discrete or continuous? Continuous? How many say discrete? Nobody. Okay. That's convenient. I can do whatever I want by posing the inverse question. Okay, so let's stick to continuous. So let's say that we draw a random number, A1. You start off at A0 equals the origin. And let's say A1 is here. It moves to A1. The particle is here. Then we draw an A2. And from here, we move to A2. So this will be A1 plus A2, right? And so on. So this distance is A2. This distance is A1. Yeah, and we keep doing this. And of course, you can also go positive. The next sample can go here. And so on. Let's say we draw these A values according to a Gaussian. Can someone guess where you will end up? So, okay, let's keep it simple. Let's say A is drawn uniformly between minus 0.5 and 0.5. Okay, you start from here and you do this. Where will you end up? No answer? The place where you end up, let's say it's d units from the origin, will simply be, I didn't mean to write this A1 plus A2 because I already gave you a clue. Despite that, you got it. So that's good. So you end up with some n sample. So if you take n steps, you will end up as the sum of the A's, right? Now, what I asked you is where do you expect to end up? So we're asking what is the expected value of D. Anyone? Zero. So the expected value of D is the expected value of this. That is linear. So you have expected value of each. The expected value of each of these variables is 0 because you're uniform in minus 0.5 to 0.5. So you expect the value to be 0. On expectation, you end up at the origin, which means you've done this really complicated walk, which is called a random walk, and you've ended up at the origin at the end of all that. Okay. Okay, so now let's look at what will D squared be. So let's say the Euclidean distance squared from the origin. Again, this is easy. You have, basically you'll end up with sigma AI, this sum squared, right? What is this? This is sigma AI squared plus 2 times a number of sums, right? 0A, 1A, 0, A1, A2, A0, A2, and all these terms. Okay, is everybody clear? We just took this, squared it, and then you get all these pairwise terms in the square, and you get just the square terms. Okay, now we need to take the expectation of this. Okay, what is the expectation of all of these pair terms? I'll make it easy. You can show that it's 0. So these things will end up with 0. What is the expectation of sigma ai squared? So what is the expectation of a1 squared? Oops. Okay, you can think about it later. Anyway, so in the end, you get this, right? And if you look at why this is significant, this gives you the, if you do square root of expected value of d squared, you get the MSE. So if you are drawing these AIs from some distribution that doesn't lead you to the origin, you can measure the squared distance in whatever dimension, take the expected values, so square root it, you should get the RMSE. This will just give you an MSE. Why is this relevant? What this means is that if you did a random walk in any dimension, you start somewhere and you keep walking by drawing random samples, you can analyze depending on how you chose these randomness. If you were uniform, you can do this. If you were biasing it with certain probability densities, you can see where it will end up, and you can see what the expected properties of this distribution are. This is a very common strategy used, again, to sample very complicated functions in certain applications. Okay, so that's just sort of giving you a brief intuition on what is a random walk. Okay, I think let's break for coffee. Oh, they haven't really announced. So okay, so I'll quickly. Only 2 people sent me some PDFs, and 1 person just contacted me about some general thing. I went through their PDFs, so that the microwave stuff seems to be. I'm not confident to say what is useful, but we can maybe. So I discuss it offline. I looked online. There's very little material on the fundamentals. Like nobody actually talks about. I could not find a good description of what is the signal, what is being integrated. Right. That paper which you sent writes some things, but they don't say why they got them. So I don't know. Is there a book for this? Or maybe the book explains everything. Do you have it with you? You have it with you? Here? No. Okay. Okay, so then I'm not confident to say what. But in general, I think from the first, so in that particular paper, the key idea was just regularization. But the interesting thing was the integral that was written was A, recursive like the integral I showed you. B, it also had a convolution in it. I don't know if you saw it. On the right side, the second integral had a convolution, which means you can potentially look at it in the Fourier domain. I don't know if people solve it in the Fourier domain, but it may be interesting to see if you can solve it in the Fourier domain, because then the convolution will become a product. But then for that, there's this Green's function and something. You need to look at the Fourier transformed Green's function multiplied by the Fourier transformed field. And this is actually not unreasonable, because a lot of imaging techniques do work in the Fourier domain. Okay, so if you look at, I don't remember, is it, so yeah, there are imaging techniques for non-microwave that do image in the Fourier domain. So perhaps there's a connection there. That's all I can tell you about that. And then for the mesh thing, so it was not clear. What is your main question? So I saw all the papers. Yeah, I'd seen some of them before. And your main question is, how do you define a feature? Yeah, but the feature, I mean, it's sort of the definition is what the different papers are about, right? Depending on what you define the feature as. So if you want to take a stochastic approach, then what would happen is you pick arbitrary points as your feature, and then you consider that as your, or you define a density over your mesh. So you define some function over your mesh where the value at each vertex. So, okay, maybe I should explain the context for other people, because we'll just discuss it till he tells us that coffee is ready, and then maybe afterwards. Okay, so the question is, there is a mesh. We saw what a mesh is yesterday. Let me say there is a circle and it has some of this, right? Now, if this mesh is densely sampled, there is no problem. It's going to look reasonably good. So the question is, if we want to remove these and represent the same mesh with fewer vertices, because there's too many, if we remove these 3 vertices, we've only removed a small set of vertices, but then this may look completely different from the rest. Whereas if we remove those 3 here, perhaps we would have gotten away with it. Or if we removed every alternative vertex, perhaps you wouldn't even notice that these vertices went away. So the question is, for simplification, what vertex should you remove? What vertices should you remove? And people have looked at it in the past. The key here is the question asks what vertices should you remove to preserve features. In this case, if you look at this, you might say these 3 are the obvious features. But in a more general setting, it's unclear what to call a feature. So one possibility to apply some of the stuff we've done would be to define, so you have some base mesh, M, you can define a function over this M, which is the probability density, that tells you what is the, or how likely is it that, let's say small m is a vertex, that M is at a feature. You can think of this as some weight that tells you what the importance is. Right? However, in your case, you're not integrating anything. Okay, so far we just have this. And then you're asking which samples should I remove. Okay, now you can think of the inverse. So when you sample, you can stochastically sample from, if this is F, you can stochastically sample from this. If you do this, then you are likely not to remove any of the features. Right? If that is the importance of the feature, and you sample from this instead, then you are unlikely to remove a vertex that was a feature. Of course, because it is stochastic, you might still remove a vertex that's a feature. So what you could do maybe is this, where the integration comes, right? So you could look at what is the expected for any given choice of vertices to remove. You can look at what is the expected simplified mesh. So you can take a standard algorithm that people do for simplification. Okay, take whatever algorithm you want. Just remove these, or take a standard remeshing algorithm. Remove these vertices. Generate a random sample from the red curve and remove that vertex, or generate n random samples according to the red curve. Remove those vertices and then remesh. Remesh and calculate the distance. For example, Hausdorff distance. How bad is this new mesh? Okay, and then once you do that, you keep on repeating this process. Then you'll get some expected value of the quality of this mesh, the mesh remeshing, or the removal algorithm, right? Now, if you change the red curve, you'll get a different expected value, right? So depending on what strategy you use to remove vertices for a particular remeshing algorithm and a particular distance measure, you should get some value, right? So it will tell you, and then you can compare them. And that'll be useful because you can compare remeshing algorithms, you can compare distance metrics, right? And you can even compare sampling algorithms. You can distribute samples according to this distribution with stratified, low discrepancy, whatever you want. So you can change all of these different parameters, and that expected value of the distance of this mesh, which is the quality, right? So the way that will work is if you have this mesh, and the real mesh that you wanted was this, then for every mesh mi, you will have some error, right? So you basically need to define this error equals distance between mi and the mesh which is the ground truth or the reference. Okay? And this will be, let's call it epsilon I, the error for the ith mesh. For a given sampling strategy, fixed distance measure d and fixed remeshing algorithm, you can calculate what is the expected value of sigma I with respect to G. Right? And that way you can explore the space of G's that are important for all these being fixed. Right? And once you find a G that you're happy with, then you can fix G, fix all of these, and just change the remeshing algorithms. I think that will be useful for the remeshing community as well, because there are hundreds of algorithms, right? And you can compare them to see how they do. So it will be a good evaluation tool, I think. And also, if you want to take all the other stuff we've done, once you've done this, you will have distances between a lot of different meshes, methods, and so on. Then you can embed them in some space, and you can see. So that way, it will be nice. You can actually get an idea of the trade-off between remeshing, sampling strategy. And so I think that may be one possibility that would be interesting. And I think that's interesting because there's a lot of this, right? There are many algorithms. And also the other thing you mentioned is you want to preserve quality. Was that you? With the Delaunay, you wanted quality. What was your goal? You want to preserve quality. Yeah, but what is error there? But you don't know the ground truth. So how do you calculate error? In this case, the ground truth is simply the mesh with all the vertices, so it's okay. But in your case, it was not clear to me if there's, and you didn't send me a reference. Okay, it's a point set. And what do you want? You want to find a mesh, which you just use Delaunay triangulation. And then what do you want to achieve? So if you apply Delaunay triangulation, you get some mesh. And what do you want to do with it? Or what do you want to achieve? Like you want to take that mesh and okay. Okay. Which is the middle step? Curve reconstruction. Yeah. Okay. 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 Okay, but what if you just apply Delaunay triangulation to the points? That's what people do, right, normally. They have points, they need a mesh. They just apply maybe Delaunay or some other. So if you do that, then the problem you're saying is solved, right? You get the mesh. You're saying you don't want to do that. So yeah. So do you understand the question? Coffee served? Ah, okay. So then maybe you can discuss over coffee. So do you understand the question? You don't want the Delaunay triangle. Cosmic. Complex. It will give you the mesh, right? But what do you mean by only give? What else do you want? Ah, okay. So that's what you're saying. So you don't want to mesh the surface. But the Delaunay and Iyer gives you also quads, tetrahedra, right? Yeah. Yeah, and the tetrahedra. Yeah. Okay. 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 You can use that to get the mesh directly though, right? Because once you get the triangulation, you already have a mesh. But if you don't want that mesh, then I see. Okay. Okay. Oh, you want to remove vertices and stuff? No, you don't want to remove it. It depends on the application. Are you running FEM with it? Okay. Then you use FEM as the error. But you're saying you want to change the way you mesh. Yeah. That's what I don't know. What is curve reconstruction? Oh, the surface is what they're calling curve. So it's all in 2D, is it? Okay, that's why they're calling it curve. Okay, I see. So you're only doing the surface first. Okay, but you can do everything together, right? You just do Delaunay, you'll get the surface and. Oh, you have two different meshes. One is the surface mesh and one is the interior mesh. The surface. You want to sample the volume. Yeah. Helidin. Okay. And if you do Delaunay, you will get.
You get those additional triangles across the.
Yeah. So you will get this, and you will get all these things.
You get the ones going out of the boundary.
Oh, I see. So you mean like that, and you don't. Okay, I see.
That's the problem.
Yeah. So that's the standard surface reconstruction problem, right? And you don't want these. Oh, so the concavity is the problem then. Okay. But I see. So you're saying if you have a concavity, then you're not guaranteed that you will get. So do you have a definition of inside and outside? Because then you can sample here. No, you don't have this idea of inside out. Okay, so that's your classical surface thing. And have you looked up? There's a bunch of work by many people, but I know work by Matthew DeBron from Caltech, where they define some distance field and then they do this moving least squares and some they sample depending on the distance field and stuff. Oh, so that's what you wanted to know. Okay. But if you'd send me the PDF, I would have explained. Do you know what paper it is? Okay. So I'll see if I find something, I'll send it. Okay. Anyway, the rest of you can go for coffee. Sorry, I didn't understand what the question was actually, even in the email. That's why.